Okay, for this next video, I want to move along with the graphs here and look at r squared equals 4 cosine theta. Now, of course, I could have done as in the last videos and chosen an a value here instead of 2, instead of 4. So instead of r squared equal 4 cosine theta, we could experiment, and we could certainly do that. But I just want to focus on this particular graph because of what new idea it's going to add to our graph drawing. Now, I was unable to get Desmos to recognize and graph the equation r squared equals 4 cosine theta. And so I had to patch this a little bit by using r equal to the square root of that expression and r equal to the negative square root of that expression. And that's actually going to benefit me, and I've chosen to color these blue and red separately to help with the visualization of what's happening. So we can hit play, and maybe I'll do that in a moment, but I want to start scrolling this a little bit manually so you can see what happens. Whenever I look at the original equation, and you can see that up in the tab, my Firefox tab, okay, if I plug in for theta the value 0, I'm going to have 4 cosine 0, which is 4 times 1, or 4. But my equation tells me that r squared is equal to 4. And all of you by now should know that that's going to have two solutions, r equal to positive 2 and r equal to negative 2. So in this particular case, r is not a function of theta. R squared is a function of theta. For each value of theta, we're in fact getting two values of r. So it's not technically a function. It's a multi-valued function if you want to divert into that territory a little bit. Okay, so when I plug in 0, I'm going to get 2 and negative 2, and so I'm expecting a point here, but also a point down here in the other direction. And as I scroll manually, you can see that I've started a blue curve over here, and that corresponds to the positive root, and I've started a red curve over here, which corresponds to the negative root. And as I scroll, what we need to make sure we understand is that both of these are being drawn simultaneously. That for each value of theta, you're getting two values of r. And as theta changes from 0 to whatever point you want, you're going to have drawn two distinct curves, and one's in blue and one's in red. Okay, so let's hit play and see that in action. Now, wasn't that a little interesting? It paused there a little bit. Now, one of the ways we saw a graph seemingly pause is when it was retracing itself. But that isn't exactly what's happening here. As we scroll and we see both of these get to 0 at around pi over 2, because cosine of pi over 2 is 0, right, and the square root of 0 is 0, and so on and so forth. What happens beyond that? When I scroll beyond pi over 2, my cosine is becoming negative. And since the square root of a negative is not a real number, I do not get a real value of r. If I consider what's happening back in the original equation, where I have 4 cosine theta, anytime the cosine becomes negative, my equation becomes r squared equals a negative number. And that does not have a real solution, r. And so where the cosine is negative, namely between pi over 2 and 3 pi over 2 in this case, we in fact do not generate any r values, and that's why the drawing paused. But when we get beyond 3 pi over 2 into that last quarter of the period, we can see the drawing begin again. And that's going to be where cosine has become positive and takes on meaningful values for r and completes the picture. And so this is an interesting experience the first time we see it, and this is yet once again an opportunity for the dynamic interaction to teach us a little bit more than what can be learned from seeing the static finished picture. If I just gave you this all in one color, it might not be obvious how it was generated, but I'm hoping that the active interaction with the graph can teach you that. Okay, so speaking of strange behavior, let's move on to something to the form like 1.1 to the theta, so using exponential type functions in our polar graphing. And here we're going to get some spirals. And so as theta is increasing, the radius increases exponentially. Okay. Now I'm trying to hypnotize you a little bit here. What I'm actually doing is not changing the value of theta, I'm changing the value of a. Okay. So as I change the value of a, which is the base of my exponential, I can increase that exponential growth of the radius. And so larger values of a are going to see that spiral unwind a little bit, whereas smaller values of a are going to see it contract a bit. Okay. If a is negative, this is not really good normal behavior. If a is 1, it's going to be a circle. And so I've limited this behavior from 1.1 to 3. You can also make it get a lot larger than 3 if you like. Now what's interesting with the spirals is considering what happens when I zoom in or zoom out. So I'm going to continuously zoom in a little bit here. It doesn't look like the graph is changing, but if you look at the numbers on the axes, you can see that we are in fact zooming in. Okay. Now this has just got to the point where theta is equal to minus 100. If I let theta go to minus infinity and to positive infinity, you would see the spiral go infinitely inward and outward. And if I zoom out, it's the same idea that the graph looks to be the same. Okay, and so there's a lot of self-similarity here. You might relate this to something like fractals, which is not exactly the same idea. Okay, but this notion of zooming in and seeing this kind of behavior is probably relatable in that same way. And so there's a little exposure to spirals that you can play with. And then I think I want to come back and look at these roses for a minute. I've set this k value to take on just your integer values. And so that whenever you see the picture of the rose, you can see that number of petals. I think it's good to play with this though and see what happens if you choose some other kind of value. Okay, what happens if I, let's say, let theta go up to, I don't know, 100 or maybe 1,000 even. That looks kind of pretty. Okay, this might remind you of a little toy called a spirograph. And so whenever I have a non-integer value of k, I can expect quite different behavior from the traditional rose. We don't call this a rose, I don't think, in that case. We have other names for it. Okay. All right, what happens if I choose an irrational value, which I don't know if this could completely understand because every computer operates in discrete language, and so it's going to truncate at some point. But what if I want to do a square root? Let's say 5 to the 1/2 power. Oh, that's a little interesting as well. Okay, so there's some ways that you can experiment beyond what I had originally intended when I created these Desmos graphs. Okay, let's get into the last one here. I know we're just about at 10 minutes, but I think we'll just finish this one up. So in this graph, I actually have multiple pictures going on here at once. I have 4 cosine theta, and I have r equal to 2. And so let's see what's happening, and ignore the details here. I'm going to come back and look at those in just a moment. But let's see what happens as we scroll. Okay, so it looks like here in the beginning we are drawing a red line, a red curve, and a dotted blue curve. And here at the red curve, I can see that that's r equal to 2. Now you might notice I've got this funny theta minus theta. For some reason I had a little trouble with Desmos allowing me to draw incrementally the circle r equal to 2. And so I had to artificially put this theta and then take it out in order to allow the drawing to take place instead of just having a static circle appear all at once. So you can just think of this as r equal to 2, and we know that's going to be a circle centered at the origin with radius 2. If I take the blue line out, and let's take the green one out as well, and just focus on the red, and I scroll this, we can see that circle appear. Okay. On the other hand, what is happening with the blue, 4 cosine theta? Well, we learned before that that was going to be part of this circles and cardioid business, and I didn't explicitly mention this type in the past video. I think you should experiment with it. But r equal 4 cosine theta turns out to be a circle as well. Now this one is not as obvious why it's a circle, and in fact it's not centered at the origin. Right? It's not centered at the origin at all. It's shifted over to the right. In my subsequent video, when I talk about converting between rectangular and polar, we will actually be able to demonstrate why this is a circle with a Cartesian equation, surprisingly. The other thing that we might notice is when we draw this blue dotted line, we get a circle, but it's completed before we get to 2 pi. And so I haven't yet seen too much of this yet. We saw a little bit with the rows where the odd k values gave us a completed picture at pi over 2. But we're now seeing that again. The circle is completed a little bit early. And so I would encourage you to go back and plug in these theta values from 0 to pi and understand why this is the case and why it seems to repeat itself after that. Okay, so let's come back and look at what is happening with this blue and this red curve. So as we progress from 0 to 2 pi, we can see that those curves are crossing at some point A. And I've taken the liberty of indicating those coordinates down here. We can discuss that momentarily. But as we proceed, we can see that at pi over 2, the blue curve is taken on a radius of 0, whereas the red curve is maintaining that constant radius of 2. Now, as we get to the point B, we can see that the red curve has maintained that constant radius of 2, but the blue curve is actually using a negative value of r. So it's actually using angles over here in the second quadrant between pi over 2 and pi to generate this part of the curve, and that's why we end up completing it a little bit sooner. Now, why do I have this point B here? Well, let's make the green one visible. As I continue to draw, what I've done is I've allowed the green curve to indicate the retracing of the blue curve. So in particular, when we draw 4 cosine theta, as we let theta go beyond pi, we're going to retrace the curve. And for illustrative purposes, I've decided to change the color, and that's why I've restricted and changed these values. The blue is going to be for 0 to pi, the green is going to be for pi to 2 pi. And so we can see that whenever the red curve is not quite finished, not even 3/4 finished, the 4 cosine theta curve is already lapped back around to A for a second time. And the significance of the point B is that it is yet another intersection of these two curves. So one curve is a circle centered at the origin. One curve is a circle not centered at the origin. It's centered elsewhere. They have 2 intersection points, A and B. But in the practice of drawing the curves, even though both arrive at A simultaneously, they arrive at B at different times, at different values of theta. When we're solving equations, this is going to play a significant role in how we solve those equations. You are used to Cartesian coordinates, which are unique, and solving Cartesian equations, sometimes by taking a y equals equation and another y equals equation and setting the expressions equal to each other to solve for x. That is assuming that any intersection points in the graphs are going to occur at the same xy coordinates, which is perfectly okay in Cartesian coordinates. But since polar coordinates are not unique, it's actually possible for the same point to be represented by different polar coordinates, and those different polar coordinates to be significant in different functions and different equations. And so when you're trying to solve for an intersection point, that point may not occur at the same value of theta for both curves. And that's going to make the algebra a little bit trickier for us in the future. At any rate, my main goal here was to have you see the curves traced in action and to see the arrival at A and the arrival at B and the differences between them. And so I think I'll stop this now and let you just play with the graphs and experiment. We're over 15 minutes, and so it's a good stopping point anyway.